So, hello everyone. I'm Simon Anghel. I work at the Astronomical Institute of the Romanian Academy. This is my team, and my team and I, we collaborate with the Paris Observatory, IMCC, on the subject of fireball networks and tracking minor planets. So, to continue this trend with AI, we're going to talk about some complementary applications to Meteor networks. So, namely cloud cover estimation. So Francois mentioned about the Freepon Consortium. I won't emphasize on it. The idea is to track all the objects that enter the atmosphere, but also to monitor the sky. So this is the network in Romania. We'll have right now 17 cameras. The whole consortium comprises over 200 cameras spread throughout more than 10 countries. This is an example of a camera. This is on top of the Astronomical Institute of the Romanian Academy on the roof right here. This is in Bucharest. This is where I work. The advantage is that all the cameras in the network have roughly the same detector, so it's easier to analyze the data. We're going to fill some gaps around here, so stay tuned for more stations, okay? Why cloud cover? So first of all, we need to assess the absorption, the solar radiation absorption. It's also interesting to understand the cloud formation process and to also improve the forecast in general. There was some previous work on this, and Lothon summarizes all of this. What's important to mention is that all of this was done using RGB images, but as you can know, most of the Meteor cameras use monochrome images. So let's see how that works out. For this, we analyzed a year worth of data on Galați. Galați is the city that I was born in Romania. So I was quite biased in choosing this network, this camera. We took all the images, 16,000 images during 1 year, and we divided it into 3 levels of cloud cover. That is, I took every image and I decided if it's a clear sky, okay, that's very few clouds or no cloud cover. Mixed sky, that can be scattered clouds or half cloudy, and cloudy sky. That's overcast or more than 80% cloud cover. You can see over here the full distribution, and also gets bluer right now in the August, September, when most of the clear sky days are in Romania, and then cloudy during the winter. This was done, all the data was divided. So right now we use 80% of it for training and 20% for testing. We get some strange clouds. I don't know what this type of cloud it is. I'll let you guess. I don't want to, but don't get influenced by this. I'll tell you the answer at the end. Okay. The idea is to put all the images into a network, and the model would automatically extract the features from it and give a prediction. For example, this is a cloudy sky prediction because we have cloud cover on more than 80% of the sky. This is a classical deep learning model. So the image would be cropped and resized and fed into a network, which first extracts a feature map based on convolution, and then a pooling layer, which will subsample each set of 4 pixels and will take only the brightest pixel and move it to the next image. So the image will decrease in size. Then again, a convolutional layer followed by a subsampling layer again. And all the pixels will be streamed into a fully connected layer, and via cross-entropy loss, it will give a prediction. And this is how the network learns. So it gives a prediction. Now we compute how good the prediction is compared to the known image. Then it goes back and reconfigures all the weights and biases, and then updates and then moves to the next image. This is how a network learns. We tested several networks. We ended up using the ResNet 34. They provided the best network for our sample and for the length of our data set. This is the prediction for one batch. This is one batch of images consisting of 32 images. You can see here that several of them were falsely predicted by the model, but most of them were right. Of course, this score is based on more than 1,000 examples, so we have an average of it. We also did it for nighttime cloud cover. This is important to assess the number of photometric nights, okay, to select the images for photometric calibration of meteors, and also to make a cloud alert for astronomical observations. We did this for the Berthelot, another station where we have also an observatory over there, also 16,000 images during the astronomical night, as well 3 levels of cloud cover. All the data was divided into three levels of cloud cover. And we get these results. We see over here that the model doesn't work that well on dimmed light images. You can see it's also hard for, it was also hard for me to detect if it's a dark sky or it's a dark sky with a veil of clouds that obstruct some of the light of the stars. So there could be some work to improve the score. And as a summary, we trained several CNN, several convolutional neural network models, and based on different optimization algorithms, we obtained the final accuracy of 91 for daytime cloud cover, and for nighttime 84%. Of course, this can be improved with a more balanced data set. We see over here that the data set was clear and over around half of the examples. That influences a bit the scores and how the algorithm computes these probabilities. And also a larger training set would lead to better scores because we'll have more examples to learn from, and then we can also implement a larger neural network. And as a future work, these methods are to be extended to more cameras over a longer time series. And also this will be compared with satellite efficiency. And the idea is we can see with all these networks of cameras, the clouds from below, the satellite sees it from above. And then you can compare this and give a better estimate of the cloud cover, and also to cross-correct the satellite measurements. Thank you.